So I'm going to introduce landslides. So I'm going to assume some basic knowledge. I'm going to give you a brief introduction to what they are, how they're formed. And these are terrestrial landslides primarily, but obviously we do see them on the seabed as well. I'm going to focus on the ones that are onshore. So first of all, what is a landslide? So a landslide is essentially the downslope movement of material under the influence of gravity. So basically the slope, essentially the strength of the slope, whatever that might be, has essentially been overcome by the effect of gravity, and the slope then begins to move down slope under that influence. So a slope can be made of rock, can be made of soil, but essentially it's that process of the failure that occurs and then the movement and transportation and deposition of that material. And that's a landslide basically. As you saw here, nice one here, my colleague gave us quite a good introduction to what landslides look like. So why do they fail? So all slopes are under the influence of gravity, so basically gravity is trying to pull them down slope, and basically we've got a situation of balance of forces. So the forces, the strength of the slope, acting to prevent the slope from moving. So to get a slope to fail, we need two things. We need preparatory factors, so factors that predispose a slope to failure, and then we need some sort of triggering event. And a triggering event might be, for example, an earthquake, a shaking of the ground. It might be an intense rainstorm, but usually they're accompanied by some sort of trigger. Sometimes what we term internal, external, so a weakening of the slope, or maybe external, so things like rainfall, vegetation changes, wildfires, for example, can trigger landslides and debris flows, and also very often human activity can also be a trigger. So I've done quite a lot of stuff, so this presentation will be available to you to remind you. But basically, this is a classic sort of diagram of a slope here. You can see a block on the inclined plane, and there were a series of forces acting on that block, really from gravity. We have what's termed the shear stress, which is resulting from the component of gravity acting down the slope, and that's trying to pull that block down that slope. To counter this, we have a frictional component of the slope. So you've probably done that, you put a block on the slope, and as you get steeper and steeper, it's fine, and you get to a certain angle, and then the block will then slide. And that really indicates that what's termed the angle of internal friction. It's this frictional component that controls the stability of the slope. So this maximum angle of stability. The properties of a slope are important, so geotechnically we call it, in terms of how a slope behaves, in terms of its strength. How strong is the slope? And we measure in two ways. We measure what's termed cohesion, and we measure this frictional resistance. And we can do some tests on the materials, I won't go into it, which will give us some values which we can use to try to understand how a slope will behave. So I've got a little diagram that shows these forces. So we have a slope, we have gravity. I'll use the pointer, you can see the pointer, you see it later. We've got gravity acting down, okay? We've got the shear stress acting to push the slope down. We've got the normal stress, which is essentially the weight of the block into the slope. And then we've got the strength of the material acting against it. So all these forces are interplaying to try to move that slope down or to resist movement. And then finally, we've got something called pore water pressure. This is the influence of water, which I'll come on to shortly. So friction, first of all, so you have probably taken some sand and piled it up. It'll get to a certain angle and start to move. And basically, most things have an angle at which they tend to be stable. Fine sand, 35 degrees, coarse sand, 40. Very angular material, 45 degrees. So you can see the friction and stability of the angle comes down to the nature of the materials. The role of water, very important. So we can have water in the pore. So here we've got a close-up of some soil. We've got some grains of soil here. We've got some voids full of air. And then we've got these little bits of water which are acting between the clasts, these small grains, producing what's termed a capillary force. Okay? So actually, when water's like this, we've got a relatively stable slope. The forces are helping to keep it together. If we keep adding water and we fill up all the voids, then basically we push the clasts apart, the grains apart, and we get a complete loss of strength. So you've probably done this on a beach. When you're building a sandcastle, what's the best kind of sand to use? Dry sand? Moist sand? You use moist sand, don't you? Not very wet sand, but it's got to be moist. The reason is because of that capillary force. You want to use moist sand. If you add too much water, then basically at some point the sand just simply becomes a slurry and simply moves away. So that's the issue of going from dry to wet to moist with capillary force, and then to saturated conditions where you get a complete failure of your material. So water is very important. Actually, water is the most important factor. So in many textbooks, you'll see the phrase that water lubricates a slope. Water does not lubricate a slope. I say to my students, do you put water in your engine to lubricate your engine? You use it to cool it, but certainly not to lubricate it. Water does not lubricate. What water does is it basically produces a force, or a pore pressure, which acts against the normal stress on the slope and serves to reduce the stability of the slope. So here we've got a picture here, a little bit, here's water level. We've got a little bit of water in between these grains, and we've got a series of forces acting to keep those grains together. When we add water, essentially the forces act differently, and we get a series of forces acting up against that normal stress. And so your stability, your slope becomes less strong, becomes weaker as a result. So adding water to a slope has a major impact on its strength. So again, this diagram, you can see gravity acting down. We can see the normal stress of the component acting into the slope. We see the shear stress acting down the slope, the strength of the material, and now we've got this pore pressure acting up against that normal stress. If you've got no water, there's no pore pressure. If you have some water, then pore pressure does exist. And you can measure pore pressure, you can calculate pore pressure. It's related to the unit weight of water and the depth that your groundwater is encountered. So landslides, there are lots of different types of landslides. I'm not going to go into all of them. I'm going to focus on the main ones. But essentially when we talk about landslides, we sort of classify them and describe them using different classification schemes. And the scheme here, which is essentially from Barnes, but basically from our geological survey, you define it according to the nature of movement and the material. Okay? Can you see that? It might be not so clear. You've got rock, you've got debris, and earth or mud, and then you've got fall, topple, slide, spread, flow. So basically we go rock fall, debris fall, and that's how we describe the motion that we see in landslides. I'm going to show you some examples of them, show you some more videos, which I quite like. So the first type of movement is not quite a landslide, it is a mass movement, but is often a precursor to landsliding. And I've done many commercial jobs where the only evidence I've found of movement are trees doing this. Yeah? I found trees doing some very strange things, got some very odd shapes, shown evidence of multiple phases of movement. Because once a tree bends, it tries to grow back vertically again, it bends again, so we've got multiple evidence of motion. So here we can see, it says this slope is moving down the slope, and the trees are bending in response to that motion. As an engineering geologist, which is what I actually am, if I see that, then I get very concerned. Yeah, I'm very concerned indeed. Essentially, a process of creeping of superficial material down slope and beginning to tip those trees forward. Here, for example, you can see the bend in these trees. Again, I said to my students, you see bent trees, you need to do some further work. So first of all, landslides are flow, essentially, where the complete loss of strength of the material essentially flows like a fluid, a viscous liquid, down slope. Its characteristics are that you have a bowl-shaped depression, a transport zone, and then some sort of accumulation zone. And obviously for this you need quite a lot of water. You need water present in some sense, or some sort of water source. Examples here, if you can just see, if I draw your eye in, you can see there's a zone here of mud. It's a mud flow that's cascading over this topography and coming out around and forming a toe here. So it's sourced behind this ridge and it's sort of flowing over the front of this, this ridge. That's mud flow, it's very fine grained. You move on to debris flows. This is from Hong Kong. Essentially sourced up here from a rock fall that then triggered a debris flow, which then flowed. You can see quite clearly here. There's two of them, following quite an intense rainstorm, which you often get in Hong Kong. Luckily, missed the major infrastructure. When you go and look in the actual gullies themselves, you can see the remains of the debris. All the fines have been washed away by the subsequent rain. But you can see evidence of all the debris left behind from that debris flow. And a debris, don't forget, in landslide terms, is a mixture of fine and coarse material. Here, a good example here is Ticina in Italy. Again, a very large debris flow. And here you can see, give an example of scale of these landslides. You can see these are houses. And again, you can see how extensive that landslide is. Again, you can see the bowl, the transport zone, and this zone of accumulation. And they can be very active. They can undergo continuous movement over very long periods of time. This is a video of, I think it's Afghanistan, and it's really good because it shows the issue of the behaviour of coarse-grained debris flows. One's going to come down that gully very shortly. And what you can see is A, look at the size of the clasts, the very large clasts, and then B, look at the clasts that are floating on top of the landslide, because they produce some very interesting sequence, because often the largest clasts, the large boulders, are actually on top of the landslide and are being carried along by the rest of the debris. So you can see them here, the very large clasts here. You can see these large ones here are actually floating on top of the finer matrix, and some of the smaller, but you can see that. Yeah? So here, another mud flow here, you can see a source area here, a lovely track coming down towards us, and we're stood essentially on the toe of that big mud flow. Another video here, a more recent one, I think this is in Switzerland, and shows a mud flow that's coming down some mitigation. They're going to put in some channels to try to divert these, and we can see the debris flows overtopping some of the bridges and beginning to spread out. I wouldn't be stood there, I'll be moving it faster. But you can see the volume of material, you can see the nature of its movement, and an idea about the amount of hazard. So from flows we go to slides. Now slides are very different. Slides occur on a very discrete surface. There's not much internal deformation. Most of it occurs along a discrete plane, a plane we call the failure surface. So here you can just see this block here is sliding on this surface, and then is basically overriding the topography as it comes out. And then we have a zone of depletion here called the graben, an area the material is now missing. So this is called a translational landslide, very common in inclined materials where you get movement parallel to the failure. So it's moving like a block and it's moving down, sliding down. Kind of things we see, so I'll show you a photograph. This is the Bindon slide in Devon, very large. So here, this block here called Goat Island is chalk. It's basically moving out here. You can see this graben here is opened up behind. So very large, you can see the scale here from the fields, large translational failure. Photograph, you can see the back scarp of it. We can see this massive chasm, which is the graben, and this Goat Island has basically slid out horizontally away from this back scarp towards the coast. And that's a translational movement that takes place. We see them quite often in weather materials. Here, this is from Sierra Leone, and we can see here, it's not so clear here, but you can see there's been a translational failure here, relatively shallow, but still quite extensive, has essentially then degraded and slipped down a slope. This is a nice photograph from Kurdistan. What you can hear is there's been a failure, but essentially the material is then completely broken up as a result of that motion. Really down to the geotechnical properties of the loessite deposits, the windblown deposit that mantles most of these slopes. So this is quite good because it shows that actually the landslides can behave in some quite complicated manners, depending upon their properties. Another video which is perhaps my favourite, which shows another translational motion. It will start shortly. There we go. You may have seen this one. It's a great video. Taken at night and shows a translation of failure from the side view. And if you watch carefully, you will see some evidence for that motion. You will at once. Oh, here he goes. Here we go. Oh, that's not normal, is it? Do trees normally come past like that? No, they don't. So obviously that slope has then slid down and it's deep enough to take all of the trees with it, all of the overburden, everything, taking it down, and basically those trees have come down with it, and obviously as it's arrested, they've basically been pushed forward. The second type of landslide is rotational. Now I found a really good video actually for this. It's very, very unique in the sense that if you look at the base of it, the failure surface is curved. Okay? Usually very, very fine grained materials normally have to be for this to occur, but essentially they're a curved surface, which means that when the thing fails, it fails in that curved surface, and you get what's termed rotation. Things rotate, okay? And things break up, and then it overrides the surface. So it's quite a unique style of failure. I've got a better video I'll show you actually, but I found this yesterday actually. Somebody did. It's a small little analog, simple experiment, just to show you what happened. You can see this curved failure surface. You can see the material. Basically, they're just pulling this small bit of plastic very slowly to see what happens. And we can begin to see that the failure along the surface is inducing settlement here and rotation, as well as the toe then is overriding that topographic surface. And that's quite a good analogue for what actually happens. So you tend to see flattening, and seeing this is now starting to tilt backwards, as well as this then kind of overrides the surface. And that's quite a good example. What they look like this, we saw quite small ones. We can see small scarps, areas of back tilting, quite sharp, quite small scale features. And then we can see some very large ones. Here are students for scale. You can just see little people here. So we can see the extent of the scarp, which goes all the way around here and past my feet. We can see these trees here used to be up there. And those trees, as you can see, are now not vertical, they're now tilting backwards. They're what we term back tilted. And the thickness of this back tilted block, we call it, is about 10 metres. And so basically those students are stood on what's termed a tension crack, which basically is telling you where the next one is going to occur. There's one type called a mudslide, which is quite unique, which is where you get sliding of this kind of like a flow, but essentially on a planar surface. And that's quite an unusual type of motion that you sometimes see. Sometimes spreading as well. These are my presentation, but I think these aren't really the main ones, so I'll skip over those. One thing I do want to say, from an engineering point of view, is something we called relic landslides. Do we know what relic means? Anybody? When I say relic landslide, what we mean by relic landslide is a landslide that's old and that's moved under a previous climatic regime. Okay? So in the case of the UK, for example, it may be moved in a period post-glacial, maybe 10,000 years, 20,000 years ago. Okay? And so we have these landslides that are present in the environment and actually can pose significant problems forwards. So it's not just the nice ones I've shown that are nice and clear and obvious, it's the relic ones you've got to worry about. Okay? When I do my commercial rep for companies and I'm doing work, it's often in response to them missing one of these landslides. Now, this is in France. I can't remember the town, but we drove into France and there's a small hospital, a medical centre at the bottom, had a huge anchored wall behind it. I mean, massive. It's huge. You couldn't understand why. So we came up behind to the other slope to look across to see why they had this massive anchored wall, to try to support the slope behind this medical centre. And this is the reason. The reason is because this entire slope here is all landsliding. But it's very subtle, but very subdued. It's quite old, but it is moving very, very small amounts. So it's not the really obvious ones to worry about, it's the subtle ones, because those are the ones that are going to cause you problems. I put some photos in here of what. So when we talk about landslides, talk about shear surfaces, very difficult to see them, very unusual. The only way you can see them is if you dig a pit into one and have a look for it, or sometimes you find them on the coast. So this is in the UK, in Warden Point in Kent, and here we've managed to find this long, can you see this long linear feature? We can see slightly weathered material above. Can you just see that? Make it out. That's a shear surface. This stuff above is moving that way on top of this stuff below. This stuff isn't moving, that stuff is. And that line is that failure surface or shear surface that I've talked about. When you get up close, it's incredibly smooth. It's polished, it's beautiful, it's slick-and-sided, it's glazed, it's kind of grey in colour from all of that orientation. So it's beautifully, beautifully formed. Here you can see very undulating surface, but again, you get your hand onto it, it's really, really beautiful and smooth. Oh yeah, there you go. So hopefully you may not be able to see, but there are on that, I can see on the screen, some faint lineations on that that give you an idea of the sense of motion that you can just about make out. And again, you can just see quite close up that surface. So quite unusual to see. You often find them in trial pits when you're doing work. You often will find these. Lateral failure surfaces, so sometimes you find these, which are the edges of the landslides moving down. It's sliding, what we term lateral failure surfaces. And these are what they're like. You can see lineations there beautifully. This is moving this way against that surface to produce that failure surface. And again, another one here. I like this one because it shows it again, but also shows you this concrete pillbox, which used to be on top of the cliff, but is now being dragged down the slope by this landslide. So that's landslides in soils, essentially. And then we'll look at landslides in rock masses, which is probably more relevant to us over the next few days when we look at rocks, because there are some characteristics of rocks which you need to look at when we're trying to assess whether or not we're going to fail. So the main thing about rocks are what we term discontinuities. Okay, and those are weaknesses in the rock, like this. So, for example, if you look at any rock mass, any type of rock, you'll find it's crisscrossed by lots of discontinuities, bedding planes, joints, etc., etc. Okay, and it's those that control, in the main, the behaviour of the rock. Here are some examples. Of discontinuity. So we've got bedding planes. Okay, we've got joint systems here. They all serve to weaken the rock. We've got metamorphic fabrics, foliations and schistose fabrics. We've got faults in rocks, and we've got open joints. All those serve to weaken the rock. A rock without discontinuities is strong and will resist motion. But most rock masses, like this, is laser scan we did one a number of years ago, but you can see you've got bedding planes, you've got joint planes, you've got all sorts of stuff crisscrossing your rock mass, which mean that you tend to get failures. Bits fall out in response to those discontinuities. So let's look at this video again that we showed you at the start. Can you see, if you look at the rock mass is what I would call what I term a dilated rock mass. The discontinuities are everywhere. Can you see them all? Yeah? And not only that, the discontinuities we can see in that rock mass are open, okay? There's clear deformation taking place. So that is a rock mass that is going to be very, very weak. You would expect it to fail. And indeed, it did fail. What amazes me is this guy here doesn't move at all. This one here. Not here, the other guy. He just seems to stand by his car. I've got to show you again. He's absolutely crazy.
Where's that from?
I don't know. I can find out for you. My colleague gave it to me and I was so impressed with it. I had to show it. It's just brilliant. But it illustrates the issue of what landslide is and what a rock failure might look like. So again, here we can see the influence of discontinuities. This is a coastal cliff in Cornwall, in the UK. And we can see what happens during failure to the discontinuities. So watch carefully. I can't think there. Here, so here we can see this is beginning to open up. We can see here it's propagating down, okay, through here, and bang, it forms a complete failure surface, and then the cliff then collapses. Yeah. So obviously, the weakness along that discontinuity, the strength of that discontinuity, has been overcome by the gravity. What can I ask you, maybe a little tricky? What other trigger factor has possibly caused that landslide?
The sea.
The sea doing what? What does the sea do to bottom of cliffs? It erodes them. So you've got coastal erosion taking place. So basically, the sea is eroding the bottom, and eventually, what we term daylighting, when that bottom of that surface is made visible, then basically that slope will then fail. Okay. So here is an example of another one of those triggers.
But also maybe it's a kind of chemical erosion.
Possibly, yeah, possibly. Weakening is like sort of internal triggers that maybe some sort of weakening is taking place. Absolutely. Especially if there's water flowing along that discontinuity, it's weathering it, like you say, then yes, almost certainly yes. But I think the main trigger would have been the coastal erosion, and then basically the daylighting to make the failure go.
May I offer a...
No, you may not.
Just a semantic point then. The coastal erosion, that was predisposing the slope to failure. Would you call that a trigger? Surely a trigger is something like maybe a big swell and the impact of waves. Do you see what I'm trying to get at? The difference between predisposing longer duration factors and some impulsive event that is a trigger, like is that a correct?
Yeah, I would say that in this case, I don't know for sure, but almost certainly a long period of coastal erosion preparatory factor, and then maybe a big storm, which then causes a big erosional event.
Well, that is, yeah, or just the impact of breaking big waves.
Yeah, I mean, normally it takes an event. It's like a big storm to then cause that big erosion, then to give you that failure. But the key thing is the daylighting, which is basically that failure surface that we observe. Let me go back. Okay. So as that failure surface is developing, it's got to daylight, otherwise it won't move. And so the erosion has allowed that to daylight, basically, further down slope, which then allows that material then to move down the slope. So the erosion probably has basically...
Yeah.
Yeah.
Can I comment on that? I would say some landslides have a specific trigger, but some others just report. So you have a big rainstorm event in Hong Kong, and you have all the debris flow starting. But then sometimes you have a big slope that is fracturing under its own weight, under the gravity fracture propagate, and they just fail without a specific trigger.
Yeah.
So you might have both.
I think in this case, well, from what I can see, the trigger probably was coastal erosion, is my feeling. But. So falls. So we're going to start with falls, which are the primary type. So these are essentially where rock detaches from a face and then drops under gravity. And it will either roll, bounce a little bit, or fall, but depending on the angle of the inclined slope. Here's an example from France, Paris in France. We can see this is the area that's failed. Can we see its mass? It's bounded by a series of discontinuities, and there's some very large class which have then fallen and rollen down the slope. You think, okay, not really a problem. Compare the size of the block to the size of the neighbouring house. Yeah. And that man, the elderly man, was told to move. He said no. So he said, no, I've lived here all my life, which is fine. They built an earth fund around that to try to mitigate that problem. And perhaps one of my best photographs, you've probably seen this photograph, is this one. Yeah? Which is have you seen this photograph? No? Yes? Yes. Oh, it's great. So up here there's a cliff, there's a rock fall, and then it rolled down this slope and just rolled past his house. Yeah? You think, phew, thank goodness for that. Oh, I'm so lucky. And then you go behind you and realise one just stopped outside the front door. Yeah? So, the landslides, these things, they have very long run-outs. So be careful. And again, past on my other favourite videos, this one. Oh, this video. I shouldn't have been back there. I'm not sure whether this might be in China or Taiwan, I'm not sure. Okay. So watch this here, watch this car now. Oh dear. Oh, so the funny thing is though, he's put his hazard lights on. He's taken the time to put his hazards on rather than getting out of the car. Yeah. Luckily, there's no fatalities there, but you get a feeling for essentially the size and the problem that occurs from these kind of landslides. I think the cars are white off right now. So
the bloke survived.
Eh?
The person survived.
The person survived, but only because that block didn't carry on, I think, and crushed his car. So debris fall here. This has happened in a place called Villaville in northern France. And the story being that I was with a colleague walking through on a field trip with students. The night before, they'd had some massive intensive rainstorms. And we were walking along, and honestly, we stood there and watched these family running into a house and running out with furniture. And we thought, maybe that's how the French do removals, I'm not sure. They run in, run out really quickly. But then we realised what happened, because further up the road we realised the house had been completely destroyed by debris fall that had washed off the top of this chalk ridge and essentially completely destroyed all the houses. So obviously the local council had told them all to get out, and so they were trying to get out as quickly as possible. So here, it's not a rock fall per se, it's a debris fall of debris which has fallen down the cliff and has demolished this house. Luckily, again, nobody was killed in this instance. So. The next type is planar slides, which are slides of rocks along some sort of planar surface. We can see here we've got an inclined surface, we've got some rocks, and they've essentially slid along that inclined surface. There are some conditions you need. You need to have what are termed release surfaces on the sides. You need to have a tension crack at the back, and the conditions there to allow the block freely to move under the influence of gravity. Again, perhaps my favourite photographs. There's one again. Those are my favourite photographs in my presentations. This is in France, going up to the town of Castellane. There's a tunnel there now, but the tunnel wasn't. Can we see these bedded limestones? And we can see clearly they are inclined towards the road, and we get a sense, don't we, that those could slide down that face. That's a planar slide. Look carefully. That is a small drilling rig, and that's a bloke with rope access, and they're drilling in some anchors into that to try to stabilise the slope. Since then, they've realised that's a complete waste of money, and they put a tunnel in here with some protection. But you can see very nicely this issue about the dip and the bed and having the space in which these are able to move. Now, the only thing that's stopping us moving are the fact that attached to this, they've got a release surface, but also friction. But you can see these small little bits have obviously slid off. They've detached along the joint and have slid quite happily down onto the road below. Another good photo in the video here. I like videos. I spent hours on YouTube. So this is a really good example of a planar failure occurring. Watch what happens. Oh, here we go. Oh, there we go. So again, inclined. Looks like, I can't say metamorphics here, and you can see the planar failure occurring along that surface. Yeah, you can see them dipping nicely. If you look carefully beforehand, you would have seen water coming from along that surface. So very high pore pressures occurring in response, and because of that, probably it's occurred after some sort of rainstorm. The next one's a wedge failure, which is a quite unique failure where we get two discontinuities come together to form like a sort of wedge, and the wedge then slides out. It's quite common, particularly in things like tunnels, excavations underground. Wedge failures are a common problem where you get discontinuities that intersect each other. I haven't got a really good photograph of one, but you can see here one discontinuity, another one, and there's a big wedge that's now missing from that section. Yeah? That's the kind of things that you'd from a wedge failure. The last type is a topple. There are two different types of topples. There's what's termed a monolithic topple, and a topple is like a drunken person, like when they fall over. Yeah. So basically, the rock basically sits there and basically just topples forward. Okay. And it occurs where you've got the conditions are you've got quite very steep discontinuities behind blocks. You get some sort of weathering at the base, and then basically that block will then begin to topple forward. An example of a topple. Watch what the people do. I always love seeing what the people do nearby. So can you see discontinuity here? This one here. You see there, it's opening up, it's enlarging, okay? And then watch this block here. It's getting wider. It's getting wider. It's going, and it's toppling. Yeah? And it's breaking its topples, and then these people start running. Oh, here they are, there they go. Yep. So that's a topple. Okay, you can see the block is toppling forward, it's very large, it's breaking up as it goes, as it deforms. We also get what's termed flexural toppling, which is actually much more complicated. Essentially, strata where you've got, you can see here, you've got like a series of vertical dominoes. Okay, what happens is with gravity, those begin to move with each other. Okay, you get a set of dominoes, you push them, they'll sort of move forward, they'll move down the slope. Here's an example here, it's from a mine, a pit in Shropshire in the UK. If you look carefully at this, I'm not sure what strata is, but you can see that as you get towards the top, they begin to tilt this way. Can you see that? So there's some deformation in those as they topple. If you go up top, they show this behaviour. So you can see that as a result of that sort of stacking, you can see that there's been movement in between each of those dominoes, and you can see the surfaces of those. As you get closer to the face, they get bigger. And again here, to be frank, I don't know why they're digging here because this looks too unstable. But you can see again evidence of this flexural toppling as those blocks are beginning to move out. So that's my last slide. I hope you enjoyed that about landslides, an introduction to them. Hope you enjoyed the videos. No one died in the making of this presentation. Okay. So thank you very much.